All right, so I'm gonna get you caught up. I have done a few days of work without streaming. One of them was this diagram right here. So I'm just going to walk you through this to get you kind of mostly caught up with what I did on the PE cough generator stuff since the last time I did get a chance to stream. So what I did here was basically I was looking at what is next for the project, and the thing that I felt really needed to be priority number one moving forward was to burn off the intermediate abstraction. Yeah, I've got two layers here. I've got the old thing I did a year ago for generating PE object files and executable files, and then I've got this new thing called Tinker, which is a lot more powerful in terms of what I can do with it. Instead of just being pure data blob generation, this is going to have the ability to do object file rewrites because it can parse an object file into the data structure, and then you can mutate the data structure in all kinds of ways and then render it back out. So it's higher level, and to implement it, it calls to the older version to do the generating part. And so the question then is, is each layer a useful abstraction to keep around, or do I want to absorb it into the new one, right? Do I want to burn off the intermediate abstraction and just have the code live inside the new abstraction entirely? And I think that I want that to happen. I think I wanted to go down to one abstraction again instead of keeping both layers alive. And so the question is, like, how am I going to get there? It did take if I remember correctly, a few weeks of iteration to build it in the first place. And there's a question here of how much of the code that I wrote is essential versus how much of it can be replaced by the new system, right? There are things, though, about laying out blocks and patching references between the data that come from this thing called block here, which I may end up wanting to keep, but I don't have a clear picture yet of which version of it I want to use and how each one it could be there's that one. Let's clarify, there's a separate copy of the block system in the old generator, and I haven't really mapped out if I need any what parts of the old generator are going to stay as they are and just get absorbed, what parts are going to disappear. Like, I'm still working through that factorization basically. Now right here I have a little bit of code sketching out what a new generator might look like. But then over here, I went through the entire old PE gen stuff, the old version of the generator, and diagrammed it out. So I'm going to walk through real quick some of the big pieces that exist in the system. First of all, there's a context, which essentially is a list of blocks. There are also lists of other things. All the stuff in this box here are the PE cough specific stuff. So there's the data sections. We have a list of data sections. We either have an image config or an object config, depending on whether we're generating an executable or object file. Then we have a symbol table, which is a list of symbols. And we also have relocation information. Each section comes with a list of relocations, as is usual. So all of that stuff, it is built into a part of a data structure separate from the context. The context is just a list of these blocks. And what ends up happening is we have I guess this isn't a part of the diagram, but we have a function that takes the obj config here, along with a list of sections, and renders out a block, right? And then blocks have a function, which you can see right here, which is to flatten. You can take a block and turn it into just straight block of data, right? A flat block of data. As a block itself, the block data structure is a little more abstract. It's not necessarily a contiguous memory block. Blocks have parents and children, and when a block is a root node in the tree, it's not considered attached to anything yet. But once it has a parent, it is considered attached. And an attached block is like the state here of whether something is attached is actually a control bit. Essentially, it's a flag controlling whether or not you can do things like allocating new memory on the end of the block or attaching new children to the block, right? These things which mutate the block, this function and this function, you can see they're notated. These that mutate the block can only be done when this is set to false, right? Once it's attached, it's supposed to be immutable. So that's one of the big rules of the system. And then it has another piece, which are these patches. And well, I guess the connecting piece here is a label is a block and an offset. So each one of these blocks represents a flat block of data, but it's a data structure with trees so that they can be assembled out of order. And then locations within blocks can be formed. And this data structure is not 100% unique. Like, it's not 100% unique coordinate system when you think about the final data structure, right? There are multiple ways to make a coordinate in this coordinate system that look different. You can have a different block and a different offset and actually be pointing at the same spot in the final map. And that's because blocks are nested, so you can have children blocks plus an offset is the same thing as the parent block plus some appropriate offset. And that's not an issue, it's just worth noting. So labels create a coordinate system, but it's got redundancies over the final flattened version of the block. And then we have this idea of patches, which are essentially saying whenever we have a patch, it's a pointer from one location to another. The reason the pointer has a from piece of data and not just a to piece of data is this is telling us where the pointer needs to be written in the final binary, right? So this isn't a pointer that runs in our program, it's a pointer in the output file. And so the blank spot in the output file where the pointer needs to be filled is this patch position. That's where we don't know yet. This is going to reference something else in the file, but we don't know where that something else's final offset is going to be until we've arranged the whole file. So this tells us as an abstract block and offset position that can be relocated where the blank spot is, and this tells us where it's supposed to point to, right? And then once everything has a final position, we know where the final position of the blank spot is. We know the final position of where it's supposed to point to, and we can fill in the blank spot. That's the idea. And then for this one in particular, there's just, a certain set of kinds. There's different kinds of patches, and each kind of patch is basically a different way to encode a pointer. So file absolute, file relative. Virtual makes sense from the perspective of object files and image files. It doesn't make sense in terms of any file, so this is PE-COF specific. Section number, section offset, also PE-COF specific, right? In the sense that it's PE-COF specific, at least in the sense that as compared to just arbitrary binary file building. Now, it might be that these are all going to be used in every operating system's version of an object file. I don't know that yet. I haven't looked at it. So when I say it's PE-COF specific, I don't mean to say that it's not also a fit for other things, but I designed this. This has been designed by a PE-COF iteration process, right? So it's specific in that way. Okay. Now, the big issue is, and as a final point, one other thing you can do is you can convert between pointers if these pointers point inside of memory that is allocated on a block. So any memory that comes back from this modifies the block that the memory is allocated on and gives you a new memory, a chunk of memory that you can use as just regular old memory. The data you leave here, this memory stays allocated until you release the whole context. But the memory you allocate this way is essentially the data that specifies what goes into the output file, right? So you can fill in this memory however you want to serialize your file, and you can take pointers into this memory, and they are interchangeable if your pointer is in fact a pointer to this memory. Then it's interchangeable with labels, the block offset representation, right? Except when we go from a pointer to a label, there are multiple labels it could be, and it picks one of them, right? And the whatever it picks, it's always going to remain valid. But the way it picks it is it uses the smallest block that it has, right? If you say here's a pointer, it doesn't scan up the tree or something. It gives you the block that is closest to owning the memory block itself. And then an offset into that. That's the one it happens to pick because it's faster. But it just gives you one of the valid labels for that pointer. When you put in a block and an offset and a label, a block and an offset, or equivalently a label, it gives back a pointer if it can at all. The other thing is in order to support that, we have one special computation in the uh, just outside containing layer that gives us the offset between a block and one of its ancestors. In order to put it another way, if the ancestor is a container, right, it's like a parent or a grandparent, and it contains this, then there is some offset from the offset of this block to where this particular sub-block begins, and then that's what comes out of this function, right? And with that, we can then implement these. That's the main idea. And the question now is, I think all of this is going to get replaced over time by the new data structure, which has the same information. But do I really need all this other stuff? Was this machinery essential to the problem, or was it overkill? I don't know. So the only way I can find out from where I'm at right now, with the information I have and the intuition I have, how well my head is around the problem, is to try it out. And if I try it out by relying on the API first, I know I will succeed at making it work. So that won't give me any information. What'll give me information is trying to write the generator without the block system and seeing if I run into a wall. And when I do, then I will learn what that wall is, and when I go to build the final iteration of the block system, or whatever, the block system plus whatever else is needed from the pieces there I just outlined, whatever survives, I will have a much clearer picture on what specific problem it's solving that makes that an essential piece of the system, right? So either way, the starting point for this bit of research is going to be to try to write this without the block system. Now, I just talked a bunch, and I'd love to get into the programming, but I'm realizing my mouth is feeling dry, and all I have is coffee, so I'm going to take a quick run to get some water, and then we can begin. Okay. So where did I leave off? I was just getting started here. Figuring out the count for the symbols and the symbol records accurately, which we didn't have before, by counting the number of auxiliary records we're going to write. So yeah, we're going to start right here. We're going to just try to serialize a block of section headers. We have cough headers here, but we don't have section headers. And then we're going to serialize a block of section data. Yeah, this is where it gets complicated immediately, because we need to know the layout. So I think what we need to do is just have, right, because I'm also missing, right here is where I guess I left off. I'm at the symbol table offset, right? I don't know the offset to the symbol table yet. So let's see if we can generate just some layout right here, and then drive the rest of the serialization from. And hello, Paging Turner. Hope you're having a happy Monday too. How are you feeling about? I'm gonna chat with. We've been. I know we're in the middle of programming here, but we've been in the middle of reading this diagrammatic reasoning book, and I'm curious overall, like not specifically the like. Since you're also reading it, what is your feeling about the book so far? Like, how impressed are you with the book? How excited does it make you feel? Is it confusing, or like, yeah, how are you finding it so far? Hey, Victor. You might have caught the tail end of a question that you didn't have the context for. Okay, so this is going to be the header offset plus the size of a cough header plus so I need to look at like a table, PE table, parse, section table, right? So cough header there, section. Super cool. That's exactly so. Paging Turner's answer. I'm gonna read it out real quick and then discuss more. Uh, There's two parts. So part one, the math is super intimidating, but I'm hoping that using the diagrams will slowly reveal how that will work. Yeah, so that's something I've been wondering about. For me, this has been like a lifelong hobby, at least ever since I have been out of college. I don't know if I was, that's not true. I was even doing this when I started college. So maybe from about the time I started college, it became a hobby just to sort of read a math textbook as a replacement for like doing Sudoku or crosswords, right? It's an activity a lot of people have, some kind of puzzle game, and it takes me a year sometimes. But there was one year I read like a 6-chapter book on point set topology, and it took me an entire year. But it was like my Sudoku puzzles, a couple of one or two exercises a night, and so this book is I'm just very familiar now with the way that mathematics is written. And this is also not quite a math textbook, it's a physics textbook. So I think the math is less than 100% rigorous, which has its advantages and disadvantages. Less busy work to prove all the theorems that support the thing, but there are certain little ambiguities swept under the rug that make things confusing. With this book in particular, I keep looking at the rules about interchanging between. So in this book we're reading, there is this idea of process. A process has inputs on the bottom as wires flowing in, and outputs on the top as wires flowing out. And then each wire has a type. And so like if you can think of type as like a data type if it's a program, or like a set if it's function, like pure set theory functions. Or maybe they could be metric spaces if it's going to be like some kind of continuous functions or whatever, right? And then again, I'm rattling off math abstractions that I'm familiar with here. There's a lot of other things you might find. Like you could think of each process as like a matrix, and the wires carrying vectors, so that it's like a linear algebra graph. But then it would be fairly limited in what the inputs and outputs could be, unless it becomes tensors, right? Tensors are this is kind of like a graphical perspective on tensors in some ways. So the too many words. Gotta skip this one. Okay. Uh, the part where I get confused is when you have a type system and you can put two types together to make a struct of those types, or to make a product type, or whatever, a compound of two types. There are things about how the type of the wire, they say that in the book, they kind of just offhandedly say that they're equivalent, but the wire counts really don't match. And so the rules about what is actually being said by a wire feel ambiguous to me and like problematic. Like, I think it'd be better to say that they're not the same. A process with one outgoing wire with A cross B is not the same as a process with one A wire and one B wire both going out. But that there's always a conversion, like there's always some kind of compounding process that can put together, and then a scattering process that can pick apart product types like that. If that were how they did it, then it would feel more rigorous, but they skip over it because it is just busy work details. But it makes me a little nervous that like weird funky stuff might slip under the rug here and there, and I don't know. So the so that's one thing I've been thinking about it. But I definitely think my advice would be, if you find the math intimidating, just following along the diagrams is going to get you a large step of the way. Like, my finding has been, whenever I'm doing math, the reason I do these exercises and I take my time with them, I'm not like super fast at them, but I put in the time to finish each one. What happens is, as I very carefully and meticulously write out my solutions, it takes forever to write them out, but I become very deeply convinced in such a way that it builds deeper and deeper into my intuition, right? I can see, like, okay, this represents that and this represents that. And so the whole, I never lose the thread as I'm carrying through writing out one of the exercises, especially like the proofs. I never lose the thread of being convinced that this step feels right and makes intuitive sense, so that when I'm done, the whole thing makes perfectly good intuitive sense. And it takes time to do it that way. But I think if you do it that way, where it looks like the book is headed to me is that it's going to build up some very sophisticated stuff. Like, I've done personally Hilbert spaces the classical way, where you go through abstract linear algebra and infinite dimensional spaces, and you talk about an inner product on that context and how to build an orthonormal basis for that, and all this stuff, right? It's very deep, abstract reasoning that goes into doing it that way, and it looks like the book is going to arrive at most of the same expressive power through this diagrammatic language that's a lot more digestible, which is super exciting to me. And the second thing he's paging, as Turner said, is, I'm approaching taking the axioms and rules of the book and trying to make a diagram editor that could work like a proof assistant. I think that's super cool. I think I've been thinking a lot about making a diagram editor while reading it too, but especially while writing down my diagrams for solutions. It's got me thinking about, in general, I don't even know. I'll just pitch you something I've been thinking about a lot. I think that most diagram systems always come with a secondary purpose. Um, right, like, you're building blueprints, you build your programming diagramming system, you build your control flow system, your state machine system, whatever it is, you build an editor with boxes and wires and an interpretation and a runtime. And occasionally I've found, like, just flowchart building stuff where you just edit the diagram. It's just data. Like, a text file doesn't mean anything until an interpretation is layered on later. There are diagram editors that don't mean anything except, here's where you put a box and where you put a label on that box and where you put a wire that goes from that box to another box. But they are extremely rich. Like, it's almost like, it's like typing too much in a Word document. It's got all the font options, and it's very PowerPoint style. I wonder about some kind of text editor equivalent, the raw information of the data structure of one of these diagrams, and an editability for that can be saved and loaded, could then have all kinds of stuff applied to it. Like, you could make an editor that saves and loads valid and invalid diagrams. I was thinking about it as simple as, it's a text system essentially, but instead of text, it's tiles, it's a tile grid, and then you have things to manage the wires that flow through that tile grid, almost like a Factorio kind of layout. So it'd be very simplified in terms of, like, it's not gonna, there'd be no free Bezier wires or anything. It'd be very discrete, and maybe that makes the editing simple at the base and the processing simple at the base. But I don't know. I don't know what the best way to do it is. But I've just been thinking about that recently. Like, what is a nice interpretation-free minimal diagram data structure? Like, what features can you afford to fit in that still make for a great editor and have all of the data structures you want? Yeah. Yeah, well, what they're doing in the book is definitely saying that this is a highly applicable thing, although they're rapidly building towards a specific process theory. So they're adding in one thing at a time over the next few chapters that turn processes into quantum physics, um, just by adding a few axioms step by step. That's how the book is going to proceed. I've read I've read ahead through a lot of chapter 4 and started the exercises, I should say. So I've kind of got an idea for the trajectory of the book now, and like most math books, it's building sort of by layers to a certain point, but I'm not sure that its point is going to be to deliver the quantum theory rather than to deliver a bunch of abstract mathematical tools, which is what happens in the math textbooks I read. But it does also make me wonder. Here's another thought I had, which is I'll bet you there are mathematicians somewhere who have already done the more rigorous, mathematically formal treatment of the same basic ideas. And I'm not saying that in terms of like ditching the diagrammatic reasoning. I think that there's probably someone who's used diagram equations, but done all the types very carefully and done all the theory building with precision. I just am curious. I don't know who that is. Like, I don't know. It's probably referenced somewhere in all the references of this book, but I'd be curious to read the underlying math if it exists. But haven't gone and looked for that yet. Yeah, I don't know how it'll go for me either, if I'm being honest. I'm confident in these first few chapters because they look very mathy. But I've had the recurring experience that in my run up to understanding quantum physics, I fall off at some point, and it moves a little too fast for me. And this is so fresh and different that especially because it's also very computational. It's closer to quantum computing than just the development of physical theories. And so I have a lot more yeah, I have a lot more confidence that it might make sense this time, but uh, I am curious to see how far I'll get through it um, before I hit that wall feeling. I'm also skipping over all of the there's advanced sections that relate process theory to category theory and abstract tensor theory, and I'm skipping over those uh, because I haven't studied either of those well enough to even treat the correspondence proofs reasonably. I think it's Curry Howard. Huh, I didn't remember that third name at all. Well, anyway. Sector. Okay, so we got a header, section headers, the end of that. Now what we want to do is start putting down some sections. Section f off equals. We're going to need a scratch arena for this. We've got one already. We're going to need one for each section. 4, 8, 12, 16, 20. Minus 1. 1 bit shifted by that many times. All right, so here we drop the first 20 bits. We keep 4. That gives us a number between 0 and 15. We subtract 1. If this was 0, then we're in trouble.